Hello students. In yesterday's class, we have discussed about nuclear structure. So in that chapter, we have discussed about what will be the design or the structure of the nucleus. Now after that, there is a chapter radioactivity which has been removed from the syllabus. So with that, I'm starting another chapter which is mass energy equivalence or nuclear binding energy. So now the first topic of the chapter is mass energy relation. Now before Einstein, mass and energy were supposed to be two different entities. Mass is fundamental property of matter possessed by every substance. Energy is capacity of doing work. Energy in matter was considered due either to its typical position or its motion. Just energy was only considered potential or kinetic. The total mass of the universe and also the total energy of the universe were considered to be separately constant. It means that energy conservation and mass conservation were supposed to be two independent laws. There were two different laws for mass conservation and energy conservation. Einstein, by his theory of relativity, proved that energy and mass are related to each other and every substance has energy due to its mass only. If a substance loses del m amount of mass, an equivalent del E of amount of energy is produced. So by losing del M amount of mass, del E amount of energy is produced. So the equation which Einstein gave is del E is equals to del M C square. By losing this much amount of mass, this much amount of energy is produced, where C is the speed of light. Now this relation is known as Einstein's energy mass relation. According to this relation, if mass is 1 kg, equivalent amount of energy which is produced was 9 into 10 to the power 16 joule. With this amount of mass, this amount of energy is produced. If we give del E energy to some matter, then according to our relationship, if we give del E amount of energy, then del M amount of mass, then the mass of that substance will increase by del M. Okay, if we give del E amount of energy, so this much amount of mass will increase. Since the value of C square is very big, that is 3 into 10 to the power 8, del M will be smaller in size or very small. For example, if we heat a substance, then the heat energy given to this substance will increase its mass. But this increase in mass is so small that we cannot measure it even by the most sensitive balance. Similarly, if we compress a spring, its mass will increase, but we cannot confirm this mass increase by any experiment. In view of the energy-mass relation, the law of energy conservation and mass conservation are no more independent law. There may be decrease in mass of the universe, but at the same time an equivalent amount of energy will be produced, which happens in nuclear fission reaction. Now sun is continuously losing mass, but we are receiving it in the form of energy. In fact, we can say that total energy plus mass of universe is conserved. Not only energy, not only mass, but total energy plus mass, both combinedly it is conserved, and it is a single unified law. The conversion of energy into mass and mass into energy can be observed at nuclear level in the phenomenon known as pair production and pair annihilation. So first I'm discussing about pair production. Now when an energetic gamma ray photon, okay, gamma ray photon, that is, photon is a particle of light, gamma ray photon falls on a heavy substance, it is absorbed by some nucleus of the substance and it gives rise to production of an electron and a positron. Suppose a gamma ray which has energy h nu, okay, it hits a nucleus Ze. Okay, if it hits a nucleus, from this nucleus one electron, sorry, this is positron, okay, one particle, there will two particles will be produced, one will be electron and other one will be positron. So if a heavier nucleus is hit by gamma photon, then it gives rise to electron. This is a beta particle, okay, beta particle. Charge of the beta particle is -1. Mass is, consider this as to be not mass, charge is -1, okay. Then with this a positron will also be released. Now it is named as positron. Now positron has the same characteristic that of electron. Okay, positron has got same characteristic that of electron, but only the charge is opposite. Only the charge is opposite. Rest every character is the same. Now according to Einstein mass energy relation, a body in a state of rest has some energy called its rest mass energy. If the rest mass, okay, if a body is at rest, not moving, and it has got rest mass m0, which is the rest mass of a body, then the rest mass energy will be E0. So E0 is equals to m0 c square. This is according to Einstein. Now the rest mass of an electron, when an electron is not moving, or a positron if it is not moving, then its rest mass is 9.1 into 10 to the power minus 31 kg. This is the rest mass. So rest mass and mass energy of an electron will be, or a positron will be, E0 is equals to m0, that is 9.1 into 10 to the power minus 31 to c square, that is 3 into 10 to the power 8 meter per second square. This equals to 8.2 into 10 to the power minus 14 joule. So this is the amount of energy produced by electron or a positron. If you convert this into mega electron volt, then 1 mega electron volt has 1.6 into 10 to the power minus 13 joule. So this is the amount of energy, mega electron energy in 1 mega electron energy is equals to this much joule. So if you convert this energy into mega electron energy, then this energy has to be divided by this particular number, which gives 8.2 in 10 to the power minus 14 divided by 1.6 in 10 to the power minus 13 is equals to 0.51 mega electron volt. So with one single electron, this much amount of energy can be produced. Hence, for pair production, okay, for this process, it is essential that the energy of gamma photon must be at least, okay, the energy of this gamma photon must be at least double of this, that is 2 into 0.51 to produce electron and a positron. If a single electron has got this much of energy, then to produce two different particle having same energy, the energy of this gamma photon has to be this much or greater than this. Okay, if energy of a gamma photon is less than this amount, then it would cause photoelectric effect or Compton effect that we are going to study in another chapter. If the energy of gamma photon is more than this, then electron and positron are produced and the energy is excess of 0. This much 1.02 mega electron volt is obtained as a kinetic energy of these particles. The kinetic energy is not distributed equally between these two particles, that is electron and positron. The positron gets more the half of the energy. This is because positron is positively charged nucleus, and when it goes out of the nucleus, what happens? Positively charged nucleus will accelerate the positron, whereas electron will be repulsive and will get retarded. Now this happens in pair production. That means two different particle is been produced with a gamma photon. Now the converse phenomenon is pair annihilation. Okay, the converse of pair production is pair annihilation. When an electron and a positron, that is electron and a positron come together, when they combine together, it gives rise to two gamma photons. Okay, these are two gamma photons. So when they come together, it gives rise to two gamma photons. This phenomenon is in which mass is converted into energy, and it is known as pair annihilation. In pair production, the energy was converted into mass. Over here, mass is converted into energy. This process is known as pair annihilation process. With this, the next topic is mass defect and binding energy. First of all, let us discuss about mass defect. Now, it has been found that the rest mass of the nucleus of a stable atom, rest mass of the nucleus, when a nucleus is not moving, is always less than the sum of the mass of its constituent nucleus. So when we add a proton and a neutron together, the mass which we get is always greater than the mass of the nucleus as a whole. Okay, so when proton and neutron combinedly, it forms nucleus. But if you compare the mass of proton and a neutron separately, and if we add that, the mass of the nucleus is always less than the combined mass of proton and neutron. So the difference between the sum of masses of nucleons and the nucleons constituting a nucleus and the rest mass of the nucleus is called mass defect. So mass defect del M is actually difference of mass. When we add proton or mass of proton plus mass of neutron, when we add these two and subtract from the mass of nucleus, the remaining very small amount of mass which we get is the mass defect. Actually, it should be same. If you theoretically explain this should be same. But when we do it experimentally, del M is always there. There is some sort of mass defect when we subtract this. Now, if you consider an atom of an atom X, which has A mass number and Z atomic number. If its atomic number is Z and mass number is A, thus its nucleus has Z proton and A minus Z number of neutrons. Okay, so nucleus has Z proton and A minus Z number of neutrons. if mp is mass of proton, mn mass of neutron, and capital N mass of nucleus, then this del m can be written as, okay, I'll write over here, del m is equals to mass of proton. Mass of proton is total number of proton multiplied by mass of single proton, plus mass of neutron is total number of neutron, E minus Z neutrons are there, and multiplied by mass of single neutron, minus mass of nucleus, which is M capital N. So this will be the mass defect. Now this equation means that Z free atoms and A minus Z free neutrons come in from infinity and combine together to form a nucleus. An amount del M disappears. The disappeared mass reappears as equivalent energy, which is, this mass appears as equivalent energy, which is del mc square. This is the amount of energy which it is produced if this mass gets disappeared when the nucleus is formed. Okay, when this amount of proton and this amount of neutron combine together, there is a mass defect, that is del m. This mass is lost, and this amount of mass creates this much amount of energy. It is due to this energy the proton and neutron remain bound in the nucleus. They combine together because of this amount of energy. Conversely, an amount del mc square of external energy is required to break the nucleus into proton and neutron. Suppose this energy combines this proton and neutron. Similarly, the same amount of energy is also required to break the neutron and proton. If you want to break the nucleus, this energy will be required. So the binding energy of the nucleus is defined as the minimum energy required to separate its nucleons and place them at rest at infinite distance apart. So this energy is known as binding energy, which is the energy required to combine proton and neutron or to break proton and neutron. So binding energy is equals to del mc square. So in place of del, I'll put this. So this becomes zmp plus A minus Z mn minus small m mn c square. So this is the binding energy. Now mn is mass of the nucleus, which is not known. Mass of the nucleus is something which cannot calculate from any experiment. Now what can be calculated through an experiment is mass of an atom. Mass of an atom, that can be calculated. The mass of an atom can be written as mxza, which includes the mass of an atom includes the mass of electron, okay, mass of electron, and also the mass equivalent of energy binding the Z electron to the nucleus. So mz, this includes mass of electron and mass of nucleus. So mass of an atom is equals to mass of electron plus mass of nucleus. So from here, mass of nucleus is equals to mxza minus zme. Now I'm putting this equation in the equation of binding energy. So zmp plus A minus Z mn minus, in place of mn I'm writing this, that is M ZA minus plus ZME C square. Now, why we are replacing this with mass of atom and mass of electron? Because mass of nucleus cannot be found or cannot be calculated. So in place of that, we are just replacing it with the things which can be calculated. So from here, from this two part, I am taking Z common. So inside the bracket, MP plus ME plus A minus Z MN minus MXZA C square. So this is the binding energy. Now MP plus ME. MP plus ME is actually the mass of hydrogen atom, because hydrogen has one proton and one electron. So binding energy is equals to Z MH plus A minus Z MN minus MXZA C square. So ultimately this is the binding energy of the nucleus. So this is the expression for the binding energy of an atom XAZ in terms of atomic masses and neutron mass. Now another one more important topic in this chapter is average binding energy per nucleon. Okay, average binding energy per nucleon. Now the binding energy ranges from 2.23 mega electron volt for a hydrogen. Okay, for hydrogen this is the binding energy, and for heavier element such as uranium, the binding energy is 1800 mega electron volt. So there is a huge difference in the binding energy of hydrogen and uranium of a smaller and heavier nucleus. So this shows that binding energy increases with the number of nucleons in the nucleus. As hydrogen has only one nucleon and uranium has many nucleons, so binding energy is different for different number of nucleons. Therefore, in order to compare the stability of the different nuclei, we require average binding energy, which is the average of binding energy per nucleon, per one single nucleon. So it is defined as average energy required to remove the nucleon from the nucleus to indefinite distance. So higher the average binding energy, if average binding energy is greater, then greater is the stability. So more the binding energy of the nucleus, more the nucleus or more the element is stable. So with this, the last part which I am going to do is binding energy curve. I'll show that from the book itself. Now this curve over here, this graph over here is known as binding energy curve. In the y-axis we have average binding energy per nucleon, and in the x-axis we have mass number. Mass number of hydrogen is somewhere here, and it increases so slowly for heavier nucleus, such as for uranium it is 238, somewhere here in between. So now from this curve many things can be understood. So the graph between the average binding energy per nucleon and the mass number of a different nuclei is a curve called binding energy curve. The fact that the binding energy curve drops down at both high and low mass number has practical consequence of great importance. So the first conclusion from the binding energy curve is the curve has almost flat maximum roughly at A is equals to 50. In between this area, that is A is equals to 50 to 80, A is equals to 50, this part and this part 80, the binding energy curve is almost flat. So average binding energy at this area is 8.5 5. So the nuclei having mass number between 50 and 80 are most stable, such as iron, which has got atomic number 56, having a binding energy of almost 8.8, that is having large number of protons. That is why the nuclei iron is most stable. That's the first part. Okay, now the second conclusion is, for nuclei having mass number above 80, if it has mass number above 80, then the binding energy curve decreases slowly and drops to about 7.6. So over here it reaches 7.6. It drops slowly after 80. For uranium it is 7.6. This lower value of binding energy per nucleon fails to overcome the Coulombian repulsion among protons in nuclei having large number of protons. So uranium has large number of proton, and uranium is a radioactive element, as you all know, and the nucleus of the uranium can easily be separated because it has less binding energy, and the binding energy per nucleon is also less. That is why the heavier atom beyond this part, beyond 200, are radioactive by nature. The nucleons can be easily separated from these elements. That is the second part. Now the third conclusion is, for nuclei having mass number below 50, if it has mass number below 50, the average binding energy decreases below 20. Below 20, it drastically decreases. For example, for heavy hydrogen, that is H2, it is 1.1. Binding energy is very less for hydrogen. This shows that the nuclei having mass number below 20, below 20, they are comparatively less stable. So below 20, the elements are less stable. Or it can be known as they are unstable, highly unstable. Now the fourth conclusion is, below 50 over here at this part, the curve does not fall continuously. You can see a sharp line over here for oxygen, for carbon, for helium. You can see a sharp line. This shows that even nuclei are more stable than their intermediate neighbors. It means that even nuclei, oxygen has got 8 number of electrons, which is even, carbon 6, and helium 2. These are more stable than its neighboring nuclei. So that is one of the conclusion. Another one is, the curve shows that very heavy and very light, very heavy and very light, having a lower binding energy per nucleon than the nuclei of intermediate masses, very heavy or very light, have got binding energy, around this uranium and hydrogen, they have got very less binding energy per nucleon. So if a very heavy nucleus be split into 2 lighter nuclei, suppose uranium, if it splits into 2 lighter nuclei, then the nuclei which the nuclei which came out after breaking uranium will have atomic numbers of this region. So its binding energy will increase. When uranium will break, it will become 2 different element. So that different element will have more binding energy than that of uranium. Hence, the energy will be released in the process. When uranium breaks, energy will be released. This method of releasing energy by breaking up heavy nucleus into 2 lighter nuclei is called nuclear fission reaction, and it is the basis of nuclear bomb and nuclear reactor also. Now alternatively, suppose if you combine 2 smaller nucleus such as hydrogen, and the binding energy will again increase. If you combine hydrogen and hydrogen, it will become helium. So the helium has more binding energy than that of hydrogen. Now whenever we combine 2 elements, in that also large amount of energy is released. and that is nuclear fusion reaction that happens in the sun and other stars, and there the source of energy is nuclear fusion reaction. So this is about binding energy curve, and this is very important. The conclusion part, which I've just told you, is there in the book also. You can just make note of it. Okay. Now in the next class, I'll start with another topic related to nucleus only. So this much for today. Thank you.